I'm a computer scientist with a, I don't know, sore throat or something, so hope you can hear me. I am currently at a startup, a small company. Used to be at Carnegie Mellon, AI faculty, and MIT in certain roles. And I want to talk about this approximate computing idea and what I think is a practical, simple approach to it. So I, about 10 years ago, belatedly realized what Carver and Mead had been saying for a long time, which was that wires, junctions can add currents, and transistors can do exp and log. These are useful operations in a lot of tasks. And a modern chip, the chips in our cell phones, right, have order of a billion transistors. They run an order of a gigahertz. So in this simple sense of operation, they're running digitally, but they have the capacity to do something like 10 to the 18th ops per second. That's probably more than at least my brain is doing, best I understand neuroscience, at least at a certain level of abstraction. But as a programmer, we only get essentially zero of it. It's 0.0000 some more zeros %. 1 out of a billion, maybe 10 out of a billion. And I'm an AI guy. I'm getting to be an older AI guy, and I'd like to see my childhood dreams come true before it's over for me. So one theory about what's made AI successful to the extent it has been or hasn't been has been the material scientists and physicists. No Einstein of AI so far, forgive me to any of my AI colleagues who may be here. And so if that's true, and deep learning is of course an example, right? The neural nets in the 60s, neural nets in the 80s, neural nets in the last 5 years especially. And so I at least think I desperately need to see that compute in the world. I don't want it going to make sure Windows runs on the next generation of laptops. So about a decade ago, I began to wonder about this, and Carver said, there's a way you can do this. Look, just become a EE, not a computer science, become a EE. Oh, but be a CMOS EE, and make sure it's analog, and do it in sub-threshold. Thank you. Thanks a lot. That turns out to be hard. At least I found it to be hard. I tried to do it. In fact, Jacob helped me try to do it. But it seemed like there were hundreds of people in the world skilled at this, and I wanted there to be hundreds of thousands of people. So I asked myself the question, could I take his ideas and try to make a, quote, normal computer? And so this is just going to tell you about a normal computer built sort of inspired by these ideas. So suppose you looked at machines that did arithmetic that was pretty close. And the reason for this is that multiply and divide circuits are very large in silicon. So as he said, look, I'm going to make life easier for the hardware people and possibly somewhere between more difficult and impossible for the software people. What would happen? And so the spec I wrote down was not the IEEE 754 floating point spec, like that. It was that. That's the spec. People ask me, well, what's the distribution of the errors? Don't think about it. Don't program to it. Don't try to figure it out. Okay, and the reason is going to be, you say this, the hardware people get a lot of flexibility to do crazy stuff to make tiny circuits. And you want tiny circuits if you're in certain fields of science, because you want a lot of compute. Now, the question would be, what happens to the hardware? What happens to the software? Is it impossible to program with a machine that operates like that? So that's what I want to tell you about, some of the results that I was able to find. So again, a lowly programmer was able to take a floating point unit, traditional digital floating point unit, and shrink it about 100x. Now that's potentially very good, and we'll look at the issues. This was using conventional digital silicon, and again, Gert helped me back in the early days, and Jacob helped me, but I couldn't figure out how to do it in analog. So I went, what people usually do, you go back to digital silicon. But it's nice because it's easy to fabricate. There's, N hundreds of billions of dollars went into the fabs to make these things. It's fast because it's digital. It's deterministic, which programmers like because debugging is, for most people, an important part of their job function. And power and cost generally roughly scale with area. So 100x smaller could be good on power and potentially cost. But you can't have anything around that arithmetic unit. You can't have a GPU's worth of control logic because then it's pointless to make the arithmetic unit be little. So I looked for the simplest possible hardware design I could find, and I took it as another related goal was, don't fight physics. Distance is energy. And in the mathematized machines that we all grew up with, there is no distance. Just access it in memory. It's there, grab it. Okay, and some people worry about cache, but most of us don't try to figure out how the caches work. So I wanted to expose that up to the programmers because it's really important if you want to get the compute power that the silicon inherently has. You have to kind of face some reality. So the architecture I took was just the old 80s mesh-connected computers where you have and this model looks like a SIMD model. The truth is the machine does MIMD. Every core can do different things, but we're going to talk about it as if it's every core doing the same thing. And forgive me, one thing I do, I've been in this thing for so long that I know what a SIMD, massively connected SIMD machine is and how it works and all, but not everybody does. So anyway, I hope it's clear. So the good model for this is I'm up here, and let's suppose I'm expensive and energy intensive. And let's say that you're all, what's a proper, unskilled labor, okay? Not so good at arithmetic. You have a little bit of scratchpad memory with you, and you all do what I yell out. Okay, so I can yell out, everybody go to location 7, get the number there, add it to what's in 9, and pass it forward to the person in front of you. Okay, that's the programming model. It's different from a GPU, where to get the performance out of a GPU, you have to actually know a lot about what's deep down inside, it turns out. It's hard to make those systems run really efficiently. This, I think I just told you the model. Okay, so you could go home and dream about algorithms that lay stuff out in 2D and move them around in space among this audience, passing notes to each other. Okay, that's the basic model. Each core in this machine, those things called APEs, is an approximate processing element. It has a kilobyte of memory. It has some registers. It has an exact integer, 16-bit, plus minus, and/or XOR shifts. So it's a PDP-8. Any of you, actually, a lot of people here are older than the normal groups I speak with, so you may remember those machines. It's a PDP-8 with this weird approximate floating point, single cycle pseudo floating point in each core. Those machines from decades back they were 1-bit machines or 4-bit machines. This one has a single cycle bang, you can do a floating point multiply with error. So this means in particular you can program up IEEE 754 floating point the way we used to, if you need it for certain bits of your algorithm. Here's a GPU. This is a little bit of an older GPU. I'll show you a better picture soon. And they have today, 2,500 cores in this thing, and it makes them a lot better than CPUs because they have 8 cores, right? And that's the first order why they're better, other things being equal. If you built a GPU-sized chip using the technology we were just talking about, the cores are here. You can't see them, I don't think. They're roughly pixel-sized, and there's about 250,000 of those on a modern chip, modern-sized chip with modern-sized silicon process. So potentially this is useful. We don't know yet. There's 2 big classes of problems. I'll get to them in a minute. Let me go fast, follow this to be fast. Some of the benefits of this kind of machine are of a mesh in this SIMD mode is, again, to use an old concept, a Fortran programmer could program it. Okay, it's just array operations. It's not multi-threaded. It's not a million cores of interacting processes. It's a serial program, a linear program, where you can say, add a million numbers in parallel, and it'll do it in one cycle. For those of you that have coded GPUs, the programming model here is you write C or C++ or Java or something you like. And in that language, there are operations that let you essentially build syntax trees, like add, of mul, of divide, and set some variable to that. And you write that kind of code, and then there's a runtime compiler that generates the machine code that has to run inside of the accelerator. And if you haven't programmed this kind of machine, which most people have not, you can go back to the 80s and there's books and papers and algorithms and all kinds of pretty clever stuff they did back then that shows you how to do interesting algorithms, vision algorithms, learning algorithms, tomography, inverse problem algorithms, a lot of stuff in this kind of mesh machine. It has a scaling benefit in that if you get a big chip and you get appropriate scissors and you cut off a corner, that can be an embedded chip. Just a mesh. There's no global structure that's different at different scales. You can build machines with thousands of cores running at sub-watt power levels. You can build a rack with 50 million cores, which is a lot if you pay attention to core counts in your machines. And actually, I was very inspired by Karl-Heinz's talk and the work that their group is doing, talking about wafer scale integration. Actually, you could build 50 million cores on one wafer. If you run the clock slow enough to get the heat out. But that may be a good trade-off for a lot of interesting problems. Compared to a GPU, if you're at the same process node, same volume, not same, but enough volume, you can get about 50x more compute per watt or gram or dollar, and you can get about 250 times better memory bandwidth because those memories are each right next to their processing elements. And I think there's a co-local thing coming up, so this clearly is that. And there's enough memory for some interesting problems. Memory is the area where I wish there were more, and there are better technologies than the SRAMs we're using. But there are limitations. So some of these are well known, and if you go back to the 80s, though, you see people cleverly getting around some of the limitations, especially in things like vision and learning. Particular concerns are, well, the I/O is slow, and roughly speaking, the chip is doing peta, and the bus is doing giga, and giga is 0 compared to peta, so you have no I/O. Okay, not quite, because the bus can also carry video. And yesterday, somebody mentioned, the bandwidth of the human I/O system might be tens of megabytes per second, maybe a gigabyte per second. That fits in standard, buses. So you can get actually interesting data in and out of these things for AI-ish problems, at least. And the memory is not a lot, but there are ways to improve it, and it is good enough for some interesting problems. I'm going to show, the next 6 slides are going to be things we've tried to do to show you how this works out. But the arithmetic is weird. So is that bad? Is it crazy? 1% error per operation, I add up 101 numbers, the thing diverged, we're dead. Maybe. So let's see. My general conclusion from the examples we've done is that it's not actually a problem very much. And it's not a problem because you can use the PhD up on stage, who costs infinitely much, well, almost, communicating with these and organizing and managing these workers, and you can get the economics of the workers and the quality of the, of the high precision traditional machine up front. Maybe an analogy is building the pyramids, lots of raw labor, but with people to notice and correct and point out the problems and refocus energy, you can often get good results. And I will show you some examples of all this now, and then just a couple slides of what we've actually built physically and where we're going. So this is an example of a deblurring algorithm. It's an iterative algorithm that inverts a point spread function, a blur function. So you see an original image. On this screen, they all look almost the same. But the original image, blurred it a fair bit, ran the inversion algorithm using standard floating point numbers, ran it using approximate numbers. I would expect to you they look all equally blurry, roughly. Turns out these are about 1% wrong per pixel compared to those, which is a little encouraging because every addition and multiplication is 1% wrong. So somehow we were able to keep it from diverging. And because of the structure of this particular problem, this inverting a linear function, there's an easy way. So a normal engineer's approach to fixing this stuff might be, I'm going to run it n times, average the results, jitter the inputs, run it n times, average the results, get a law of large numbers, decrease in error. So run it 100 times, I'll get 1/10 the error, square root of n error. Turns out, in this problem, there's an easy way, took a day to dream up, to use double the time and get 100x lower error. So it's just one example saying there may be more clever ways than just jitter and average. And that's what most of these examples are aimed to show you. Here's one done at MIT at the Media Lab. It's just a standard Gaussian mixture model background subtraction. So it's a megapixel image. At every pixel, you keep 5 Gaussians. They're supposed to represent the background, the most likely things you've seen in the back, in the image. And when something moves through, it might tend to push those Gaussians around, but after it passes, they'll tend to return back to whatever's in the image. And then you just say, when you get a new frame, does it match one of the Gaussians or not? If it doesn't, it's white. If it does, it's black. So it's called background subtraction. It's used, you could use this in Target to see, are people hanging around which end caps in the store, right? You can do motion detection. So this algorithm needed no changes to the code at all, and 14 pixels out of 1,000,000 are classified differently, and anything beyond that in the vision pipeline had better deal with 14 pixels that might be right instead of wrong, or wrong instead of right, or who knows. The algorithm is just a complete hack, right? Just seems to work in practice somewhat. So the point is, no code change, same results. Here's some work done with Takeo Kanade's group. He's a pretty good known vision researcher in computer science at CMU. He was interested in couple of cheap cell phone cameras real near each other and doing stereo vision cheaply. No LiDAR, no $50,000 laser scanning thingy, just a couple of cell phone cameras. So there are algorithms to do this. They did some work. The results were, these are the input images up top. There's the button. This is standard reconstruction. This is approximate arithmetic reconstruction. 80% of the pixels came out the same, and the ones that didn't happened where the scan lines have no contrast, so you can't know the depth to the thing because there's nothing to distinguish when you do the matching. Here's one. So I stayed away from math problems for a long time. Sandia eventually persuaded me, let's try to do 2D Ffts. And this is for synthetic aperture radar. So it turns out you can do 2D Ffts. You do 1D across, and then you do a separate pass 1D down, and that composites into a 2D FFT. We did that. We got some spattering of these overflows, these white speckles in the image. Not good. So I slept on it a night. Next day I said, well, what happens if I do it in the other order? First do down and then do across. So you also get some speckle, not many. Take the min of the images. Essentially, all the speckle essentially always drops out. Twice the compute on a much faster underlying machine, you get results just like what they normally get. This is another defense application for a drone, a tracking. So somebody marks a spot, in this case, I keep losing the button. In this case, this vehicle, and this system computes Gabor filters, edges, all the pixels in the neighborhood of this original spot on a given frame, goes to the next frame, and all the region computes these features. You match the features in the current frame against the feature in the next frame. You say, what's the best match? That's where the thing moved to, and you iterate. So that's a pretty compute-intensive process, because there's like 10,000 pixels in this little green box, and you got to do it at reasonable frame rate, and there's nearest neighbor matching going on. Anyway, the point was that in pre-hardware analysis, this approach, this machine, looked like it would run about 89 times faster with a 70th of the power. And that's 6,300 times compute per watt advantage. This is what encouraged DARPA to say, okay, I want you to build one and see if this is nonsense or if it's actually going to run. And this, by the way, runs on a small, cheap embedded chip. Okay, so finally, the last example at MIT, we did some deep learning with a speech group. They did MNIST, which is, you probably know, is a standard vision task, and then they did some speech tasks, and there's a master's thesis describing this. So for the forward classification, running the networks forward, the results were identical. You could train in floats and run in approximate, or train in approximate and run in floats, or floats, approximate. It was essentially the same results. Backwards, this is, as you run through your training iterations, your epochs, which are very slow, the error falls down something like this. But the interesting thing, of course, is that this scale is epochs, not time or energy. And if you change it to energy or time, the curve really looks like that. And for the people that are spending a month, they come in the morning with an idea about a network they want to test, a trick. They start it. It takes 3 weeks before they've got their training results. And obviously, they've forgotten largely what they did and don't care about it anymore anyway. It's way too long. So we need a lot more compute, at least in this deep learning field. And the same thing works going forward. So in an embedded system, a cell phone or an earring or a car, you can run these deep networks efficiently. Okay, so briefly the hardware and then the future, and then I'll be done. So we built these chips, and they work. Here's one. I brought it. It actually works. They have 2,000 cores in them. They're about a half a centimeter on a side. That's very small, well, relatively small for a chip. A GPU is maybe 25 times more area than this chip. This is done in a 40 nanometer silicon, which is a few generations old now. Modern laptops will have 14 nanometer. That's 8 times denser silicon. These things run at about a couple hundred megahertz. They get about 200 gigaflops per watt peak, which is a few times better than the most recent GPUs that have come out. But they are built using more modern processes, and this is built using an older one. We're putting 16 of these chips on a board. We're hooking it to a Linux system on an ARM. We're building 5 of these for DARPA, so that's a 170,000 core system. It produces about 68 teraflops peak. More interesting is it has about 68 terabytes per second memory bandwidth, which is a lot higher than the corresponding GPU system, because they're going out currently over a bus to a separate memory. And any time it's the opposite of this co-local computing, and it kills us. If you want to get the real power out of silicon, I don't think you can use that kind of architecture. This system's going on the net probably this summer for people to explore. There's some folks who have first dibs on it, but DARPA is being very generous in saying anybody that has an interesting project is welcome to try and use it. And we also have these little embedded systems that are available for certain groups. This stuff for the commercial people out here, this stuff is in patents. So there's a image of the chip. My company, another company in Boston, Cadence did our physical design. Moses did our MPW run, and Global Foundries did the actual silicon. Here's a modern GPU. That's a current high-end GPU, desktop GPU, done in 28 nanometer. Here's this chip we built. 3,000 cores, 2,000 cores. That one runs faster, but it's 100 times the power driving that machine. And so the final slide here is we need to continue building up our tools and libraries. I'm working on a deep learning library to make it easy for people in that field to try things. Building up the community of users, starting with the ones I showed you on a prior slide. People doing real applications this year, I hope. Again, for any business person, my interest, I'm a scientist, and I'm only doing this because I want the damn computer, basically. And so my preferred path is license I want big systems, and I want them cheap. So I want to license this. I hope to license this out to some big company or companies so that they can make a ton of money and scale it up. And a little thin slice can come back to science, I hope. And I'll show you what I want to use it for. The next gen hardware, this was done on a shoestring. For chip design, we did this on $1 million, okay, plus a lot of sweat equity of people that didn't think they were going to have to sweat at all. But for $1 million, we built this thing, and that's very, very small. People talk about $50 million being the right amount. So there was no feedback loop in this thing. So we went through the stages, built it. Oh, that's how big it is. Oh, darn, we should have done X. Well, next time. So I'd like to have a next time. Optimize the design, use a modern silicon process, build them closer to GPU-sized chips. And I think we can get multi-teraflop per watt systems. I think we can get these servers that have 50 million cores, and now I'm suspecting we can get wafers with 50 million cores, maybe. And my personal wish here, I think this permits practical and compact billion-core machines, right? And that turns out to be a lot. Maybe you don't think about it too much, but that's a lot of cores. A data center might be 10 million cores, a big data center. They're different cores, but these are pretty good cores for a lot of purposes. My goal is to get them into the hands of scientists, students, because that's where the breakthroughs are going to come. And I'd love it if a grad student could wake up at the middle of the night, say, gosh, I wonder what would happen if I did that, and go and have a 100 million core machine to run it on by morning and find out. So I think it's practical. I think it's really practical. I think we could do this now. So that's the story. Thank you.
Take a question.
You can take 1 or 2 questions while our next speaker set up. Sirius, do you want to come up?
Hello. I was a little confused about how your cores worked. You describe having 512 memory elements, each 16 bits. Are they, a rapid set of related questions. Is that digital memory?
Yes.
Okay. But you're conducting your floating point operations in analog.
No.
No.
All digital.
This is all digital.
Yeah. It's a very ugly, it's the kind of circuit that would come out of a genetic algorithm. It's just a horrible mess, but it works.
Okay, so you have a very simplified FPU then that cuts some corners and ends up having error because of it?
Yeah.
Okay.
Yep.
Very quick question. Very good work, by the way. Now, how did you get a 100x improvement in performance in just 2x time? You mentioned this very briefly. This seemed like magic.
Okay, so you do the deblurring, approximate. You get something that's, let's say, 1% wrong in the pixels. And it takes you, hundreds of cycles. So it takes a fair amount of time and energy. You send that result back to the CPU. You have it blur it using the point spread function in high precision. You subtract it in high precision from your sensor input. You get an error image. The values are about 1% of the original. Send it back over. Another 100 iterations. You get back the corrections to the corrections. You bring them back and add it in high precision.
Taking advantage of the residue.
I'm sorry?
You take advantage of the residue, right?
Yeah, yes. I mean, it's one. Each of these algorithms has its own ways of fixing things or dealing with it, just like algorithms have each of their own ways of accomplishing their goals. Just got to be a textbook, 99 tricks for dealing with lousy math.
Thank you.
Okay, thank you.